Hi guys, welcome back to Calculus with Mr. Robeson. Today we are going to look at limits. So we're starting the first probably new thing for most of you in calculus. So we're going to look at what's a limit and how do we find a limit. All right, so to do that we're going to investigate this little function here. So we're going to look at the graph of f of x equals x to the third minus 1 over x minus 1. So in our last presentation, we went over how to graph this. We're going to press y equals on our calculator. We're going to type this in. We're going to put the top in parentheses. We're going to put the bottom in parentheses. And then we're going to press graph. And we should get some sort of picture that looks something like that. Now I've changed my window a little bit. Looks like I'm going from -3 to 3 and going up 1, 2, 3, 4, 5, 6, 7. So maybe from like a half to 7 or something like that. But there's our graph. It looks pretty close to a parabola. And there's something weird happening right there. So then my question to you is, what's the domain of this function? So hopefully you remember what domain is. I know you went over it in Algebra 1, you probably went over it in Algebra 2, you probably went over it in pre-calculus. But domain is just any x values that you can plug in to the function. Right? And if you can't plug in those x values, then that's not in the domain. So for this guy, our domain would be, let's see if my pen's going to work for me today. Where is it? X cannot equal 1. Because if we plug in 1, that would make this bottom equal to 0. So we want to know, when does this equal 0? Because it can't equal 0. We add 1 to both sides. We get x cannot equal 1. So if we look, here's 1 right here. And if we go up to the graph, not very straight there, but there's where our problem is. Yep, right at 1. All right, we can write this a couple different ways as well. We could also write this as from negative infinity all the way up to 1 with a parenthesis here. And then we start on the other side of 1 and we keep going all the way up to infinity. That's just another way we can write our domain in interval notation. All right, so that's what's happening at 1. We have some sort of hole. So the interesting point on this graph is 1. Everywhere else, we just plug in. Like if we want to know the limit as we go to 0, we just plug in. We get that value. I think it's 1. If we want to know the limit at -1, we plug in. If we want to know the limit at -0.5, we plug in. If we want to know the limit at 7, we plug in 7. Because it's a smooth curve at all those spots. Right? So that's the value that it goes to at all those spots. But right at 1, there's an issue. So let's take a closer look. All right, so we can't say f of 1 equals 3. That doesn't work. All right, because there's a hole there. All right, there's a big open hole, so the function value is actually not defined. All right, but it looks like it was going to 3. All right, so this is where we introduce limits. All right, so instead of saying f of 1 equals 3, because it doesn't, we say the limit as x goes to 1. So this is the limit as x goes to 1 in f of x. That is how we say this little phrase right here in math. The limit as x goes to 1 in f of x. So what we end up doing to find this limit is we check what happens on both sides. So close to 1 on both sides. The word we use is infinitesimally close. So like we move a tiny, tiny, tiny little bit each way. All right? And there's 3 ways we can do this. All right? So way number 1, we can look at the graph, which we were looking at a minute ago and had a pretty good idea of what it was going to. It was going towards 3. Numerically, we can use our table, which we learned how to do in the last presentation, or we can do it analytically. All right, so this is the fun way here. This is using algebra. So we'd be factoring and canceling out stuff, or multiplying by a common denominator, or a conjugate, or some sort of way to end up canceling stuff out. That's usually the most difficult way, which means it's the most fun way. All right, so our loose definition of a limit at this point, we haven't actually defined it yet, but as x approaches some number, so some x value, in this case 1 is that number, the limit is the y value the function approaches from both sides. So it has to approach the same value from both sides, otherwise it will not exist. So let's go back to ours and let's look at it graphically. So graphically, we can just zoom in on this little section and we can see both sides. It's going to the same value just on the other side of this hole, and this hole is really infinitesimally small. So for both of these, it looks like it's going to 3. So it looks like our limit here is going to be 3. All right, if we do it numerically, that's our table of values. So we pull up our table. All right, we can put it to start at 1 and put it to 0.01 for our table set and just arrow up and down, and it looks like 2.97, 3.03. We can make the table step even smaller if we want, but it looks like this is getting closer and closer on both sides to 3. So it looks like our limit's going to be 3, which agrees with our graph. All right, analytically, so this is probably the harder way. All right, so like I said, this is a more fun way. So we got to try and factor this top. So this is the difference of cubes. So this is 1 to the 3rd power right here. So what we can do then is we can say that this is x minus 1 in parentheses times the first guy squared. Switch the sign. Multiply the two together. 1 times x is just x. And then plus, always plus the last guy squared. So 1 squared would be 1. So that is how we're factoring the top to get this. Once we get that, you should notice there's an x minus 1 on top and bottom. Those will cancel out nicely. And once they cancel out, that gets rid of the trouble spot. Remember, 1 was what we couldn't plug in, and that was, if we plug in 1, that was 0 over 0 for both of those. All right, so that removes that discontinuity. So whenever there's a spot when the bottom equals 0, we call that a discontinuity. That's a removable discontinuity. We also sometimes call that a hole. Fancy way is removable discontinuity. So what we're left with is just the limit as x goes to 1 of x squared plus x plus 1. All right, we remove the problem area, so now we could just plug in 1. If we plug in 1, we also get 3. So everything worked out to the same on that one. All right, so that was one where the limit had issues. That's one where we had a problem. We had removable discontinuity. All right, for these two, we don't have any issues. All right, the graph of 3x minus 1 is just a line. There's no holes, there's no problems. All right, it's crossing the y-axis down here at -1. Its slope is 3, so it's going up pretty steeply. Should have arrows on both ends here. So there's the graph of that. If we plug in 2, so maybe 2 is here, we're just up at some value here. There's no hole, there's no problem. So if we just plug in 2 here, this is just going to be 3 times 2 minus 1. So 6 minus 1 gives us that limit is going to be 5. All right, same with our sine graph. So hopefully you remember what a sine graph looks like from pre-calc. So sine starts at 0 and goes up, and then goes down, and then goes back up. Hits the axis again here at 2 pi. Again, we're always using radians when we're working with trig in this class. So this is 0. We go back the opposite direction. It's just the same shape backwards. So this would be -2 pi. This would be -pi right here. All right, it goes up to 1. It goes down to -1. -1. All right, so as we approach 0 from both sides, it's just this point right here. This just goes to 0. So we just did both of those graphically. We could just plug in and do them analytically as well. All right, when our functions are a little bit more difficult though, so use a table to numerically estimate the limit at x equals 0. So if we tried to plug in 0 here, that's going to be a problem. So if we plug in 0 here and 0 here, clearly the top is 0. So the top is going to 0. The bottom, we get the square root of 0 plus 1. The square root of 1 minus 1 also goes to 0. So that is a problem. All right, so let's just look at the table instead. So we can type this into y equals. Remember, parentheses around the whole bottom. And if we check on what's going at 0, on one side we've got 1.9995. The other side we've got 2.0005. If we change our table step to even smaller, these numbers will get closer to 2 and closer to 2. So it looks to me like this is going to 2. All right? And if we look at the graph, again, we're looking right here at this point that's disappeared. There's our hole right there, and it also looks like it's going to 2. All right, so that limit was 2. All right, with this guy, this is what's called a piecewise function. So f of x is equal to 1 if x is not equal to 2. So everywhere but 2, we're up at 1, and when it's equal to 2, it's at 0. All right, so do we have a graph here? Yep, there it is. All right, so everywhere except for 2, it's up at 1, and then at 2, we're down here at this point. So that means as it approaches 2 from both sides, as x approaches 2 from both sides, it's up here. All right, so it's up here at 1. So that means the limit as it approaches it from both sides. So that means the limit as it approaches it from both sides, limit as x goes to 2 of our f of x function here is going to be 1, because from both sides we're going to 1. All right, so it doesn't matter what happens exactly at that value, the limit is what happens as it goes to it from both sides. All right, so that was our brief introduction to limits. We'll come back on our next episode and do a little bit more with limits. We'll talk about when limits don't exist in some other tougher cases, but we just went over what is a limit and how do we find a basic limit.